Okay, example number 4. We're once again back to ray diagrams, so now for lenses. We're asked to find graphically the image and then also mathematically. So we'll start off with our ray diagrams. We have a converging lens, and the object is placed here, a distance of 50 centimeters from the middle of the lens to where the object is. This F1 represents the focal point. You'll notice now there are two focal points because you can see two curved surfaces on this lens, but these are both equidistant. This is what we're going to call the primary focus in the converging lens, and this will be the secondary focus. Okay, so one thing I do before I start constructing the ray diagram is I like to draw a little dash line right down the middle here. And the reason I'm doing that is because rather than showing the refraction when it occurs at this surface and then at the second surface, we're just going to show the refraction in the middle. Otherwise, it'll get too complicated to do at both surfaces. So what we do is we draw the ray as if it goes straight to the middle, and then we only bend it at one place. But in reality, it's actually bending both entering and leaving. But when we do the ray diagrams, we simplify the process by drawing this dash line and showing the bending only at one location in the middle of the lens. Okay, so let's go ahead and start the first ray. We want to draw 3 rays to find out where this image is. Okay, the first ray is going to go parallel from the top of the object parallel to the principal axis. So here we are. There's my ray going through here with my ruler. And then once it gets to the middle of the lens, then it's going to refract through that focus right here, F2. And you'll notice that I'm drawing these little arrows on here to show the path of the light. So that's ray number 1. Let's go on to ray number 2, which is the light that goes from the top of the image right through the center of the lens. Okay, so then you're going to draw a line going through the center of the lens, right about here. And then one more ray that goes from the top of the object, but now uses the other focus, F1, first, going through that focus, getting to the middle of the lens, and then at this dashed line, and then it's going to go parallel to the principal axis. And if you've done everything properly, then hopefully these 3 rays all intersect at one place. So that light coming from the top of this object is now going to be showing below the principal axis, which means that this image is going to be inverted here. And if you look at this image has 3 characteristics that you can note. The image is, first of all, real. Now, this is important to realize. Now the real images are going to be on the opposite side of the object. So now they're on the back end of the lens. That's actually a real image because these light rays are passing through here and really intersecting at this point. It also appears to be smaller than the original object, so it's smaller. And last thing is you can see that it's upside down, so it's inverted. Okay, so then we can go ahead and calculate the mathematics. It's the same as what we were doing before. So you can write the lens equation, and you can write in the focal length, which is 20 centimeters, and the object distance, which is 50 centimeters. And this gives you an image distance of 33 centimeters. And that means it's a positive image distance. This distance is right here shown. SI should be coming out to roughly 33.3 centimeters. SO, by the way, is the distance from the object to the middle of the lens, and that was initially stated as 50 centimeters. And the focal length for here and here are both 20 centimeters. So just so you get a little bit of perspective in terms of the distances. We also could check the magnification by using the magnification equation, negative SI over SO. That is negative 33.3 divided by 50, and that gives you negative 0.67. So this tells you 2 things here. Since it's negative, that means that it's inverted. Since it's less than 1, that means it's smaller for the magnification. That means the image is smaller than the original object. It's about 2/3 of the size of the original object. And lastly, it's 33 centimeters behind the lens, and when you're behind the lens, that's actually a real image. Okay, now let's take a look at what would happen if you were to put the object right at the focal point. Okay, we'll start with the blue ray, that top ray that goes parallel to the principal axis to the middle of the image, or the lens. Actually, we should show this dotted line. There we go. And then now we're going to show that ray is going to refract and go through focal point 2. And then now if we show ray 2, the red one, from the top of the object going through the center of the lens, it's really going basically essentially at 90 degrees of the surface, so it doesn't refract. So hopefully you can see that these two rays are parallel, which means no image is formed. Or you could say the image is formed at infinity. So we can go through this mathematically and plug things in, and you'll see that when you have 1 over 20 for the focal length, 1 over f, and then 1 over 20 for the object distance here, and then 1 over si, you're going to get 1 over si equals 0. Si will be infinity. So the image essentially is formed at infinity, which is basically impossible. So that's why we say there's no image. And the magnification, which would be negative si over so, that's negative infinity over the object distance of 20. That's going to give you negative infinity. So that's infinitely large size image. So if you were to put this object at the focal point, you will have an infinitely large object at infinity away. And you would actually have to be looking from this side to see that infinitely large image of this particular object. Let's go on to part C now and see what happens when you put the object at 15 centimeters, which is somewhere in here. Okay, so turn to the page. I'll first start showing that dashed line through the center of the lens. And now we can start doing our ray diagrams. First ray from the top of the object towards the center of that lens. And then it's going to bend towards, remember it's converging, so it's going to converge towards focal point 2. And there's the direction of the light. And so now the next one is going through the center of the lens, which looks like that. And hopefully you're starting to see that these two rays here and here are diverging away, so there's not going to be any image that's formed on the back of the lens, which tells me that there's no real image when you put the object between the focal point and the lens. And the next ray comes from focal point 1, but it's really the light is emanating from the object. So I just drew this dashed line to show you where my ruler is lined up. And so the light is coming from the top of this object towards this middle of the lens. Now I know the lens is not there, but I'm going to assume the lens is large enough to go through there. And then this light is then going to go off parallel. Now you see all three of these rays are diverging away, so your eye is going to look at the refracted rays and you're going to extend backwards the refracted rays back on the same side of the object. Remember, only dashing backwards the refracted rays, just like you dash the reflected rays backwards in mirrors. So I'm going to take this particular ray here and I'm going to draw a dashed line backwards here. Roughly, that should be a little bit higher. And similarly, if my eye was looking from this end, I will also dash that one backwards here, again in line with the refracted ray backwards here. Something like this, roughly. And we're going to do this for the red ray. Okay, right here, like this. And roughly about there. Hard to say. Obviously, I'll have to extend this black one a little bit. So you can see that this eye, if you're looking from this angle or from this angle, they're all going to be looking back here and seeing that this image is right here. So the light from here is going to appear to be basically, you will see something like an image that is larger. It's upright and it's on the same side as the original object. However, if you put a screen here, you're not going to get a real image because these are made from dashed lines, and so your eye just thinks that the object that you're looking at here. Essentially what part C is an example of a magnifying glass. So now let's go through the mathematics to determine what are these distances. Remember the equations we can use: 1 over SO plus 1 over SI equals 1 over F, and the object distance is given as 15. Focal length is 1 over 20. This gives you an image distance of negative 60 centimeters. So this negative 60 centimeters means it's in front of lens. So this distance that we just determined here is SI, and this was SO. SO again was 15 centimeters, and then SI we've determined as negative 60 centimeters. You'll notice there's a negative sign because it's on the opposite side, or it's actually the same side as the lens, and those are considered virtual images. Okay, so next thing, so virtual image. And the next thing is to describe the magnification and tell us whether it's smaller, larger, or upright inverted. So we use m equals negative si over so. That's negative 60, well, negative of negative 60, divided by the object distance, which is 15. This will give you positive 4. This tells you two things. The image is upright. We know it's upright because we have a positive here. And it's larger because it's 4 times larger here. This should be roughly 4 times the height of the original object. Okay, now we move on to part D. This is a bit of a kind of an odd example, but we're putting the object on the right side. Now you could consider this object as a real object and draw a ray diagram normally backwards, but we're going to consider this as a virtual object. It's kind of an odd case, but let's take a look at it. I'm going to do the mathematics first, and then we'll figure out where that image is supposed to be. So using our equations that we had before, we're going to find the image distance. So we have 1 over negative 40 plus 1 over SI equals 1 over 20. This gives you an image distance that is positive 13.3 centimeters. That means it's going to be in the same side as the object. And then our magnification negative 13.3 divided by negative 40. That gives you positive 0.33, or about a third. So this tells us that the image mathematically is real, smaller, and upright when you compare it to the virtual object. And so now we're going to consider a virtual object. That's an object that is located on the other side of the lens here and is not a real object. The incoming rays are going to not diverge. They're going to converge because this is a converging lens. And we're going to draw a ray diagram kind of like what we were doing before. So ray 1 has to be parallel to the principal axis at the same elevation as the object. And so what I've done is showing where I'm lining up my ruler to the top of the object and parallel to that principal axis. And now we're going to show that incoming ray coming in here towards the lens. And then the ray will refract through the center. And the next ray is now going to be going along this, line up my ruler right along here. And I'm going to draw a ray coming in through here towards the lens. And then the ray will refract and go parallel, basically doing the opposite of what the blue ray was doing here, that first ray. And for the last ray, I'm lining up my ruler right along this edge through the center of the lens to the top of the virtual object. And I'm drawing a ray right along there that's going straight through, and it does not refract because it's essentially going at 90 degrees to the surfaces. And finally, now we can see where the image of this virtual object is, which is right here. And so you can see now that the object was a virtual object with a negative 40 centimeter distance, but the image in the end is a real image with a positive distance of 13.3 centimeters. The image is real because these light rays do intersect. It's smaller than the virtual object, and it's upright, the same orientation as the original object. And that's it for this example.